Hello folks, today we are going to look at some dilution calculations, including the equation that is given to us on page 3 of the chemistry reference tables, as well as understanding why we're doing the calculations that we're doing because of conservation of mass. So the equation that's given on page 3 of the chemistry reference tables, M1 times V1 is equal to M2 times V2, has molarity of the original solution and the volume of the original solution being set equal to the molarity of the new solution times the volume of the new solution. So these little subscripts 1 and 2 are just referring to moments in time. So the initial conditions and the final conditions. And the reason that these two things are set equal to each other is because of conservation of mass, which says that particles can't appear or disappear. In this case, we're talking about the solute particles. As long as you don't spill any of the solution, you're not going to lose any solute particles, and no new solute particles are just going to appear. So what's being conserved or preserved is the number of moles. And dilution is kind of a vocabulary term here. And really all it means is that we are adding solvent to the solution. We're spreading out the same number of solute particles amongst a greater volume of the solution. We're not really changing the solute. We're not changing the identity of the solvent. We're just changing the amount of solvent. So what do problems like this look like? Our first example says 0.100 liters of a 12 molar stock solution need to be diluted to 0.750 molarity. What should the new volume of the solution be? So stock solution is a phrase that you're going to see fairly often in this type of problem. And stock solution is the liquid that sits on the shelf in the back room. It tends to be very concentrated. They have very large molarities. And we use a little bit of them at a time. And we keep our solutions stored at such a high molarity so that they take up less space. And then when we need some, we take them out, we add solvent and dilute them down to the concentration that we need for our work that day. So the thing that stays the same between the stock solution and the dilute solution is the number of moles, as conservation of mass says. So when we're solving these problems, our first step in our procedure is to find that number of moles. And then we can look for whatever it is that the question is asking for in particular. So the first step is to find our number of moles, and we have the molarity and the volume of the original stock solution. So what I'm going to do is I'm going to take my number that's not a ratio, I'm going to take my number that's not a ratio, 0.100 liters. I'm going to set up my railroad tracks. I'll put that in the top left. Underneath will be left blank since it's not a ratio. I'm going to write 12 molar as a ratio, so that will be 12.0 moles for every 1 liter. That will enable liters to match on the diagonal, canceling out, and I will be left with the number of moles in the solutions in this question. So if I do 0.100, I need to multiply all the numbers in the top in the numerator, and I can divide by any numbers in the denominator, and I will get 1.2 moles. I'm not going to worry about rounding right now. We round right at the very end before we report our final answer, and this is just step 1 of 2. So now that I know the number of moles, I can then calculate what the question is looking for. And in this step, they are asking what should the new volume of the solution be? So for step 2, I am going to use the dilute concentration and the number of moles to find the new volume. So I'm going to start with the number of moles, since that's the number that's not a ratio. Put that in the top left corner of my railroad tracks. I'm going to use my dilute concentration, which is 0.750 moles for every 1 liter. And that will match moles on the diagonal, allowing it to cancel, and I can plug into my calculator, multiply all the terms in the numerator, and divide any terms in the denominator. And my calculator says the answer is 1.6 liters. This is my final answer, so I need to check on significant figures. Going back to the original problem, I've got 3 significant figures behind the decimal in 0.100. I've got 3 significant figures in 12.0, and I have 3 significant figures in 0.750. But my calculator answer only has 2 significant figures. So in order to increase the number of significant figures without changing the value of my answer, I'm going to add a 0 to the end. Since it's on the right of the decimal, it will be significant and enable me to have 3 sig figs in my final answer to this question. So, in order to take our stock solution down to the correct concentration, we just need to add solvent until we get to the volume of 1.60 liters. Now, this is a 2-step procedure, and as you have probably noticed by now, scientists like to be lazy, and they would rather not do 2 steps. And this is where the dilution calculation comes in. So if we look at the problem, we can identify the initial conditions, the first original stock solution, as having a volume of 0.100 liters and a molarity of 12.0. We can identify the concentration of the dilute solution the next moment in time as 0.750 molar, and the new volume as being our unknown. So the other way to solve this problem is to do a little bit of algebra. And so what we're going to do is we're going to take m1 times v1 is equal to m2 times v2, and we are going to isolate the new volume that we are looking for here. So having identified v2 as the variable we are interested in, we're going to move m2 across and diagonal into the denominator of the other side. So this means we have m1, v1, and now m2, our new concentration, is in the denominator, and that will give us the volume of our new solution. So railroad tracks time, we're going to need the initial concentration and volume to start us off. So we have 12.0 moles for every liter in the stock solution. Draw our long horizontal line. Our initial volume for that stock solution was 0.100 liters. And then because our new concentration has been moved into the denominator, I am going to need to write the 0.750 in our denominator. We have some units that match on the diagonal, including the moles and the liters. So those will all cancel out, and we will be left with liters as our new volume. Do notice that in this alternative method, doing everything at once, we still have all of the same numbers from our stepwise procedure in the same places, right? 12 up top, 0.100 up top, 0.750 down below. We've just kind of mashed the two sets of railroad tracks together here. And when we plug this into our calculator, again, multiplying all of the terms in the numerator, dividing by all of the numbers in the denominator, we get the exact same 1.6 liters, which we would round also to 1.60 liters so that it has the correct number of significant figures when we report it as our final answer. So you get the same result regardless of which way you do the calculation, whether you do it stepwise, finding the number of moles first and then doing whatever the question is looking for, or if you use the equation and do everything all at once. So we're going to look at a couple other examples. And we'll solve it both ways. So what volume of 15 molar stock solution is needed to create 5 liters of a 0.25 molar solution? So we're being asked what volume, being asked to calculate what volume, and then we are given the initial concentration as well as the final volume and final concentration. So our first step in our stepwise procedure would be to find the number of moles. And we're going to do that using the values that we have that are paired up. So we'll take the 5.0 liters of our final solution, and we will multiply that by the ratio here, 0.25 molar, or 0.25 moles for every 1 liter of solution. Liters match on the diagonal, canceling out. So into our calculator, we will multiply all the terms in the numerator, divide by any terms in the denominator, and this will tell us that we need 1.25 moles of solute. Then we can find what the question is looking for. In this case, the initial volume, the volume of the stock solution. And so we're going to use this number of moles that we just calculated to start our railroad tracks, since it is not a ratio. We'll put that in the top left. And then we're going to use the molarity of the stock solution. It is 15 moles for every liter. We'll need to flip it over so that moles matches on the diagonals, and they will cancel out. Into our calculator, we will say 1.25 divided by 15 times 1. We get 0.833 repeating liters of solution. Significant figures, we've got 2 in every number here. So that means we'll keep the 8 and the 3, and the 3 would say to round down. So we will report 0.83 liters as our final answer. If we want to do this all at once, using the dilution equation, M1 times V1 equals M2 times V2. We are searching for the initial volume, so we're going to have to move M1 down into the denominator, which will leave us with V1 is equal to M2, V2, and in the denominator M1. So we have our final concentration, 0.25 moles for every liter. We have our final volume, 5.0 liters. And we have our initial concentration, but it is flipped over, so the 15 moles needs to go down below, and the 1 liter will go up top. We have units matching on the diagonal, moles and liters, which will leave us with liters as the unit of our answer. We multiply everything on the top, divide everything on the bottom, and we get the same 0.83 liters as our final answer that we got in the stepwise calculation.